In this session we'll learn how to sketch the diagram of shear force and bending moment for this given problem. Before we start, we always need to calculate the reactions, the RA and RB, and the possibility of having another reaction here. We'll check that. And to do so, we have to go to the equilibrium equations. If you remember, the equilibrium equations are the sum of all forces in x direction is equal to 0. The sum of all forces in y direction is equal to 0. And sum of all moments about x, y point is equal to 0. These are the three equilibrium equations that we learn to use in static. And of course, when we have an intersection of two unknowns, because this is an unknown, this is unknown, like we said, this is unknown. So we have three unknowns. So the intersection of two unknowns will be the point where we'll take the moments about. So we'll do that to calculate the reaction B. So we'll do sum of all moments about point A is equal to 0. So what we have here about this point, so this force will rotate in this direction, which is clockwise, negative, and this reaction will rotate in this direction, which is counterclockwise, and is positive. So these are the only two. Of course, this will not be included because it passes through the point. So let's do that. So we have plus reaction at B multiplied by the distances from here to here, which is 28, multiplied by 28 feet, minus this one, which is 25 kips, multiplied by the distance from here to here, which is 20 feet, is equal to 0. So that will lead to, if we isolate RB, is equal to 25 multiplied by 20 is equal to 500, divided by 28, and is equal to 17.85 kips. This is the first reaction. So if you want, you can update this by saying 17.85 is equal to this. Now we'll continue. Now we'll use the sum of all forces in y direction is equal to 0 equation now. With this one we have RA is upwards, and we have 25 is downwards, and RB is upwards. So we'll do plus RA minus 25 kips plus RB is equal to 0. And here we just remind you the rules are, if the force is in this direction it is positive, and this direction is negative, upwards is positive, downwards is negative. So continue here. So RA is equal, we don't know RA, it is unknown, so RA minus 25 kips plus RB is already calculated as 17.85 is equal to 0. So RA is equal to 7.15 kips. So this is the second value, and you can go ahead and update this value here equal to 7.15 kips. Okay, back to the horizontal. So we apply the sum of all forces in y direction is equal to 0 equation, in which, if we have suggested the direction of the force, this is R, this was supposed to be RAY, and this is RBY, this will be RAX. So RAX, we have only RAX plus RAX, and there's no other force, so this is equal to 0. So we have proven that this is equal to 0. Okay. Now back to the main issue here, which is to plot the shear force diagram and bending moment diagram. So if we would like to sketch any diagram, say any diagram like so. So this will be this axis, y-axis will be, say for example, for shear force, and this horizontal axis will be for distances. So what we're trying to do here is we'd like to calculate the shear force at a distance, say for example 7, then shear force at a distance of 15, shear force at distance 20, shear force at distance 24, and then until we get to 28. And then we have these points, 1 point, 2 point, 3, 4, and then we draw the diagram. This is the idea. So the idea again is to find the values for shear force. These are shear force, right? And these are the distances. So after that we sketch the diagram. That is the task that we intend to do. So let's move on to calculating. Now that we know the values here, let me move to, so we have here, this is the 7 feet, and this is 15 feet, and this is 24 feet distances. So again our diagram will be as and say this is the this is the x, which is distance, and this is shear. So this is shear force, and this is distance. Now let's update. This value is 7.15 kips, and this is 17.85 kips. We calculated this the previous page. So if you look at the diagram or the forces here, so if we take this to be this distance is 7.5. Say this distance is, so we're trying to represent the forces by distances. So this is 7.15 millimeter, inch, whatever. And then if we move in this direction, you'll see there is no force changing this until you hit the 25. The 25 will bring this down by 25 units, or millimeters, or inches, or centimeters. So meaning that this distance is, as we know, it is 7.15, and the remaining distance here is equal to, if you go ahead and subtract 25 minus 7.15, you will get 17. The remaining distance here is 17.85. Same millimeters, we are using millimeters for a scale. And then back, the shear force continues like that until it reaches this point. So this is the path of the sketch. And then at this point where we have the RB, so this will go up by an amount of 17.5, which is the reaction here. So this is the shear force diagram. This is the shear force diagram. Meaning that if you would like to know what is the shear force at this point, then you measure this distance and say it is this much kips. If you want to know the shear force at this point, you just measure this distance and you will know how much is in kips. At this point, measure this distance and you know how much it is in kips minus. This is positive, this is negative. So this is the how we calculate the the shear force. In this case it is straightforward, so we don't need to do much calculation. The only calculation we'll do is at this point, which is, you say 7.15 minus 25, and this is equal to 17.85. Of course we are measuring in millimeters maybe, so this will be kips. That's what we got. So that's for the shear force diagram. But if we would like to do the bending moment diagram, in the case of bending moment diagram, because the shear is just a force and we have the forces in front of us, but when we talk about bending moment, the bending moment is here's the bending moment sketch. So for bending moment, the bending moment, as you remember, the definition of bending moment is force multiplied by distance. So it is the bending moment, or moment, is equal to force multiplied by distance. Now in the case of shear force, the force was going up like that and continually there's no changes until it gets here and goes here and this here. But in the case of bending moment, this force, if you take the bending moment at this point, this is a combination of force multiplied by distance. If you go to this, force multiplied by distance, as the distance is changing, it means that the bending moment also changes. If I take the bending moment here, it will be this force multiplied by this distance, so we are changing. That's why we need to do the calculation for all of these as we go. So again, we'll put the scale, which is, in this case, we'll have this will be the bending moment, this will be the distances. So the x will be the distance, and this will be the bending moment value. So I suggested here these points, suggested 7 feet, at 15 feet, at 20 feet, and 24 feet, and then at 28 feet. But you might ask why these distances. You could go ahead and change them, make it 6, make it 18, whatever. You are just plotting a diagram. Keep that in mind. You are just trying to sketch a diagram, so the number of points will be up to you. That this is not going to be defined by me. It is you who will define it. So my task here is I would like to see what will be the bending moment at distance of 7 feet, and what would be the bending moment at distance of, so I will go and say what is the bending moment from left at distance of 7 feet is equal to how much is this. Now before I continue with this, my question to you is, what is the bending moment here and what is the bending moment here? The bending moment at these hinges is equal to 0. Just keep that in mind, and our calculation will prove that. So let's try with so if you want, you can do this in a more to be easier. So it means that this is the part that we are talking about. We're taking the moment at this point, and this point is a distance of 7 feet, and this force is 7.15 kips. So this will rotate in this direction, so meaning that the bending moment at distance of 7 is equal to minus 7.15 kips multiplied by 7 feet is equal to minus 50 kip dot foot. That is the first value. Now let's move to the next. We have a distance of 15 feet is equal to how much? So again, same sketch. So I have and this will be again same thing. It is 7.15, and this distance from here to here is equal to now 15 feet. So again, I would like to get the value at this point. Straightforward. Again, this rotates in this direction, so it is minus 7.15 kips multiplied by 15 feet is equal to minus 107.25 kip foot. Here's the other value. Okay, move on to the next. So if I would like to do it at distance of 20, moment at distance of 20 feet, is equal to how much? And the sketch is same, so it will be minus 7.15 kip multiplied by 20 feet is equal to we don't 20 feet, because at 20 feet is this point, so you might ask, well, shall we include 25 or not? Well, the calculation can prove that to us if you want to, because if we have 25 included, then the distance between the force and the distance, the point of action here, so it will be, let's say it's minus 25 kips multiplied by how much is the distance at this, because the 25 is sitting at a distance of 20, so there is no distance, meaning the distance is equal to 0. So you might as well in the future not even include the 25, because it is sitting on the point. When the point passes through the, when the force passes through the point, it makes no rotation, so the moment is there equal to 0. So get it, this equal to minus 143 point, no, but there's no point here, so that's kip foot. Again, if we would like to do this the sketch, maybe it will look like this. It is at this point where we have the 25, we're taking the moment at here, and this is the only force we have, so this will rotate in this direction. This has assumed direct direction, but the distance is 0, because this distance is 20, so this has no distance, this point has no distance. So now back to the other point, a distance of 24. Now that we are distant, we went beyond, so I'm going to take, and this is 7.5, and this is 25, and these distances are and this is a point that we don't take moments about. So this will rotate in this direction, and this will rotate in this direction. So this is negative and this is positive. Let's do the numbers now. So moment from left, a distance of 24 feet is equal to how much? So it will be minus 7.15 kip multiplied by 24 feet, because this is the distance, plus, now we have distance for 25 kip multiplied by 4 feet is equal to how much? So with this we get this value is equal to minus 71.6 kip foot. Okay, so now move on to the last point, which is moment from left, a distance of 28 feet. Now is equal to how much? We need to prove that this is equal to 0, because we said the hinges are equal to 0. The moments at the hinge are equal to 0. So it will be the same equation as this one, the sketch also. So we have minus 7.15 kip multiplied by 28 feet plus 25 kips multiplied by, this is the distance, which is 8 feet, multiplied by 8 feet is equal to how much? And this is equal to 0. So we are correct. Now that we have done all of these, we would like to start to locate these points. So we have a distance of 7. Let me just highlight the ones the values I've calculated here, and this one. So a distance of 7, I have value of minus 50. Now for bending moment, most of the books, they will use the minus above the line, above this line, and the positive down. These are just some sort of a convention. So we'll do the same thing. So minus 50 is somewhere, say here, and then so this is minus 50. Then the next is 107. A distance of 15 is 107. So it is here minus 107. I'm just ignoring the decimal. Point of 20 is equal to minus 143. Minus 143. And then a distance of 24, it is minus 71, so it's going down, minus 71. And point of 28 is going to 0. So you see, these are the points. So we need to connect these points. So you could connect the points like straight line or curve, we don't know, but we have a proof as from the equation as how this will look like. Now if you look at all the equations here, we try to derive an equation. If you look at the distance of 7, the equation is 7.15 multiplied by 7. Now if you look at 15, 7.15 multiplied by 15. So the thing that is changing in this equation is these ones. These are the x's. Okay, so if we take this as an equation, I could write this equation as 7.15 multiplied by x. That is the equation, and that is, if you remember from calculus, this is a linear equation. A linear equation means line. So all we need to do here is, this proves to us that this is a line. So I represent this by a line like that and a line like that, and that will be the bending moment diagram. And this is again some sort of a rule. So a point load will result in linear equation. This is the bending moment diagram for this example.